we start with 15 grams. Okay, 81. Decays in such a way that the mass remaining after t days is given by. Finally, they write m of t. Thank you. Is 15, which is the initial mass, times e to negative 0.087 t, where m of t is measured in grams. Yes, we know that. After how many days is there only 5 grams remaining? Yes, we have to solve for t. So we are told the remaining mass is 5. After how many days did that happen?
So 5 is
Exactly. The mass today is 5. Very good. That's it. So this is 1/3. We divide both sides by 15, and I get this. 87t. And yes, you're right. Natural log 1/3 equals negative 0.087t. So then t equals natural log of 1/3 over what is left in there. So, say it again. Yes, 1/3. Yes, the answer will be positive because if you remember the graph of log, past 1 is above the x-axis. Below 1, so it's the top will be negative, of course. Very good. Good point. So we have natural log of 1/3. And divide that, don't forget parentheses, negative 0.087, close, that's it. So roughly 12.6 days. We can say approximately 13 days. It's less than 13. Okay, the last section deals with the same thing, what we just did. So we just have to choose more problems. So this is the last section of this chapter, 4.6. More word problems. That's it. Yes. Tony, you want to start?
Yes.
Okay. You want to come here or over there so nobody bothers you?
Sure. Stay there.
As long as. Okay, more word problems. Page 350. Page 350. Bird population, fox population, fish population again. Population of a country, bacteria culture, population of a city, bat population, deer population, frog population, bacteria culture, population of California, and world population. So we are talking about the exponential growth model.
Let's do batty over here.
Okay, very good. Exponential growth model. Let me write it again for you. The amount of time at time t is the initial amount times e raised to kt. Nothing new. Continuously compound interest. Same thing. Same formula. Right? A equals p times e raised to rt. Now A stands for amount. A0 is the initial, what we start initially with. K is the exponential growth rate, like we had before, the annual rate, and T is time. Okay, so we want the bat population. Okay. The bat population in a certain Midwest country was 350,000. So in 2009, so that's problem 10 on page 351. In 2009, it was 350,000. and the observed doubling time for the population is 25 years. It doubles every 25 years. Okay, part A. Find an exponential model n of t equals n0 times 2 raised to t over a for the population t years after 2006. So 2006 represents t equals 0. Now, first thing I have to address is this model can be rewritten in terms of number. Same thing, right? So it's, forget about this, the doubling one for a second. So if we don't use a, we can use number. So it will be n of t equals n0 times e to kt. So don't get confused, they mean the same thing. So instead of using the notation a, I can use the notation n. Okay, so that's really the same thing. Number. Okay? Good. So find an exponential model, n of t, which is n0, the initial number, for the population t years after 2006. So, okay. So what is this little a? What does this little a represent? And I want to draw your attention, if you want, for a second, to go back, if you have it, if you have your text. On page 341. At the top of page 341. The exponential growth doubling time. We rarely use this, but since it's in the problem, I have to show it to you. I will not test you on this, because what we normally use is the exponential growth, relative growth rate, which is this model that we've been using all along, where n of t is the population at time t, n0 in the initial population, r is the relative growth of rate of growth, and time t is time. So, but if since the problem is asking us to also look at the exponential growth as the doubling time, let's talk about it. Again, I'm not going to test you on the doubling time. So, if the initial size of a population is n0, which we do have, and the doubling time is a, lowercase a, it's this denominator of the power, then the size of the population at time t is this, where a and t are measured in the same time units. Minutes, hours, days, years, whatever they are, but they have to be measured in the same thing. So they're asking us to come up with this equation in which we are given the initial population, but the initial population for us is not at time, however, where am I? Okay, page 351, correct. It's, if you look again, it says 350,000 bats in 2009. So this does not constitute N0. It constitutes N0 for 2009, which makes 2009 T equals exactly. Okay, so then N of T equals N0, which is 350,000, times 2, T is T, and it doubles every 25 years, T over 25.
So N0 would be 350,000, not.
So, and then T, yes, and then T will be T plus 3. Only because they're asking us for 2006, right? So they want us to come up with a formula, not for 2009, where we have the initial value and so on and so forth, but they want us to find the formula for T, but 3 years later. The initial 3 years 3 years prior to that, right? So this was 2006. 3 years later. So if we want to, that's what it said. One more time. Find an exponential model for the population T years after 2006. T minus 3. Very good. Okay, part B. Find an exponential model, and this is what we are interested in. Part B. Find the exponential model n of t, which is n0 times e to rt, for the population T years after 2006. Okay, so the initial population is still 350,000. E, we do not have, bless you, we do not have the rate. In some books it's R denoted by R, in some books it's denoted by K. So let's stick with R because that's what they have. So we do not have R. But we do know that in 2009, we have a point, right? When T is 3 years, the population was 350,000. So R times T. So I do know that when this means that n of 3 equals 350,000. In 2009. So knowing this, I will be able to determine R. So 350, as we did before, this is our 350,000 equals 350,000 times E raised to R, which is unknown, times 3. Say it again. N of 3 is 350,000. E to 3R equals 1. So natural log of E to 3R so 3R equals 0. So obviously we have to determine what happens in 2009, which is when T is 0, we have 350,000. And based on that, we determine R. So the initial is at T equals 0. In 2009, we have 3 years later. This is the initial population. We know it doubles every 25 years. We have to go back in time. We have to go back in time since we know it doubles every 25 years, and we have to determine what was in 2006. So in 2006. So if we know that in 2009 it was 350,000, we have to be able to determine the population in 2006, knowing that it doubles every 25 years. So if we start with 350,000, 25 years E to R times 25, this will be doubled, 700,000. We have to start with that. It's the only way of determining the rate. So in 2009, the population was 350,000. We know that it doubles every 25 years. So 25 years later, after 2009, 25 years later, this population will be doubled. So then 2 equals e to 25 times r. So 25 years later, the initial population doubles. So this over this is 2 e to 25r. Natural log equals 25r, and we finally get r. Natural log 2 over 25. So let's put in the graph and calc. We'll check everything in a second. So natural log of 2 divided by 25. So the interest rate, not the interest rate, but the growth rate is, so R equals 0.0277. So now I have the model. So N of T equals 350,000, that's the initial population, times E to 0.0277 T. And this is the relative growth model.
For a year.
We can determine for any year you want. Yes. So for example, when T is 0, when T is 0, I get for 2009, that's where we started, the initial population. 2009, when T is 0, I get N of 0 equals 350,000, because e to 0 is 1 times this. Now, if I want to go back in time, when T equals -3, which is in this case 2006, N of -3. I have to get smaller than 350, but smaller than half of 350, right? Because if I go back 25 years, then I will get 350 divided by 2, which is 175. So I will get somewhere between 175 and 350, but closer to 350 because I'm only going back 3 years. So let's see what we get in that case. We have 350,000 times E in parentheses, point, I'm going to put minus already. Minus, is that minus? Does it show? Yes, I see it, it's minus. 0.0, oh, I can do the previous answer, yeah. Previous answer times 3. I get less than 350,000 as expected because I'm going back in time 3, but definitely more than half of it, which would have been 175,000. So the population in 2009, 6 I meant, is 322,065. I cannot, when it comes to number of people, bats, mice, I cannot round up, or I can only round down, no matter what. Sketch a graph, we can do that, of this population. Estimate when the population will reach 2 million. When the population will reach 2 million.
Can you use the graph?
Yes, and I can use the graph by graphing 2 million, I'm sorry, 2 million, and then go graph. I can. Yes. So we're asked to find the time when the population reaches 2 million. So what do I do now? Right, I have to clean it up. So 200 over 35 equals e to 0.0277 t. Right, so I apply natural log of 200 over 35 equals 0.0277 t, and finally t equals natural log of 200 over 35 over 0.0277. Ready? Okay. Natural log 200 divided by 35, close the parenthesis, and divide by 0.0277. I cannot recall the previous answer because then it will recall this, not. So it's roughly 63 years. So the bat population will increase from 350,000 in 2009 to 63 years later to 2 million. Did I put enough zeros? Yes, I did. Okay? So what does this mean is, well, assuming that they still have room where they are in the habitat where they are, because otherwise if they are restricted, they may not get to that amount. Okay, so let's take a look at bacteria culture. Please choose a bacteria culture. 13, 14. So then we can look at cooling a soup, like 25. Yep, I like 25. And finding half-life and more problems with radioactive decay. Yes. Which one? Which bacteria culture are we looking at? Which one?
13.
Okay, very good. 13. Culture starts with 8,600 bacteria. So what is this? Obviously N0, the initial value. After 1 hour later, the count is 10,000. Find a function that models the number of bacteria N of t after t hours. That's our first question. So we have to find N of t, which is N0 e to R. They use R. We're going to use R. It doesn't matter. You can use K. It doesn't matter. The notation is not important. So I do have this. So for now, I know that N of t equals 8,600 times e to RT. That part I know. But now I have to use this. What does this say? 1 comma, when time is 1, the number is 10,000. How do I put this in this equation? How do I put this point in the equation that I have? Of course. Yes, exactly. 8,600 times e raised to r times 1, because t is 1. Very good. We know how to solve this. Yes. I'll divide both sides by 86, so it's 100 over 86 equals e to r. And then apply natural log. So r equals natural log of 100 over 86. And now with this, I have the model. I only have to determine natural log of 100 divided by 86. 15%, a lot. So R equals 0.1508. Now I have the entire model. So the model is N of t equals 8,600 times e to 0.1508 t. That's what the problem was asking us to do. Part A. Part B. So find the number of bacteria after 2 hours. Exactly. So N of 2. So 8,600 multiplied by E to I want parentheses, to 0.15. Oh, I can recall the previous answer. Multiply by 2. We're not going to get the same answer if you... Oh. What did I do?
That's what I asked.
Oh. Okay. So it was 0.1508 times 2 plus. Okay, 11,627. This is the number of bacteria in 2 hours. Okay. After how many hours will the number of bacteria double? What is the double of the initial? Two times this, but let's write it as 2 times 8,600 and not multiply. And you'll tell me why I write it like this. Right. I have to simplify by 8,600. So then natural log 2 equals 0.1508 t by this. So then t equals natural log 2 over 0.1508. So natural log 2 divided by 0.1508. Roughly, yeah, 4.5, yeah, indeed, 4.6 hours. Okay, let's move on. Yes, any questions, please?
Yeah, quick one.
Yes.
So in A, when we solved for R, what was that
We were asked to find the model.
right, so we find the model.
Yes, in order to find the model, we have 2 questions to answer. The initial and R.
Okay, and then R was
The relative rate of growth.
the rate of growth.
Yes,
So after
15.08%.
0.15 of an hour, it's 8,600.
Here?
No, I was just, so after 0.1508 of an hour, there was 8,600 bacteria growth. That was that.
This one? No, this one says that the growth rate is 15%.
Oh,
Yes.
okay.
Okay, so let's look at cooling the soup and then radioactive decay. 25. This is Newton's law of cooling. Okay, a hot bowl of soup is served at a dinner party. It starts to cool according to Newton's law of cooling. As you see, it has exponential function in it. So its temperature at time t is given by T of t equals 65 plus 145 times e raised to negative 0.05 t, where t is measured in minutes and t is measured in degrees Fahrenheit. So minutes. Good. What is the initial temperature of the soup? How do I find the initial? Always. When t is exactly. So I have to find t of 0. T of 0 we can do by hand. How much is 0 times negative 0.05? How much is e raised to 0? How much is 1 times 145? 145. How much is 145 plus 65? Part B. What is the temperature after 10 minutes? That I cannot do by hand. 65 plus 145 times E in parentheses, negative 0.05 times 10. Close the parenthesis and enter. Should it be higher than 210 or less than 210? I know it's a silly question. Right, because the exponent is negative, right? It's a decreasing. Good, 153 roughly. Part C, after how long will the temperature be 100? Do you see that the pattern repeats in all these problems? Okay, they're all the same. How do I determine how long it takes for the temperature of the soup to go from 210 to 100? So 100 equals 65 plus 145 e to negative 0.05 t. What will be the first step? Exactly. So then 35 equals 145 e to negative 0.05 t. What happens next? Yes, I have to. And of course, like we did so many times before, I have to apply natural log. And then t equals natural log of 35 over 145 negative 0.05. So natural log 35 divided by 145, close the parenthesis, and divide in parentheses by negative 0.05 and close. So in about 28 minutes, the temperature will drop from 210 to 100. Okay, so this is the last application, radioactive decay. The formula is the same, but this time we use M because we are talking about mass. Everything is the same, but since it's decreasing, there is a little negative in front of R. Oh, this is the model. We haven't picked yet. We haven't picked it. I'll let you pick. Yes, please pick anything you want. So the radioactive decay model starts on page 351 with problem 17. It's, if you see, look right there, right between 16 and 17, it says, these exercises use 17 to 24 through 24. These exercises use the radioactive decay model. And this is the radioactive decay model. So let's start with and I would like to talk about half-life before we choose. Okay? So what is half-life? If I start with M0 and the mass in time gets to half of M0, okay? So let's see what happens here. T will be what is called H, half-life. So again, we are ready to start. Okay, so let's see what happens. So in order to get the initial, now instead of doubling it, in order to get the initial to be half of it, then m0 divided by 2 equals m0 e to negative RT. I will divide both sides by m0, of course. I get 0.5 equals e to negative RT. I apply natural log to both sides. And then I get t equals natural log 0.5 divided by negative r. This is what it's called H, or half-life. However, I don't want to memorize this. You don't have to. It will not be difficult to figure out how to determine this. But yes, this is a formula. The formula in your text takes into account that this is, so natural log of 1/2 is the same with negative natural log 2. Would you agree? How do I know? Because this is natural log of 2 to negative 1, and I can bring negative 1 in front, and that's how I get negative natural log 2. So then t, so you can remember it like this if you want to. I don't recommend it. Or you can remember it by replacing this by negative natural log 2 divided by negative r, so it will become natural log 2 over r. And this is the half-life. I personally don't even think about it. I read the problem and I determine it, or I use it when I need it. So there is no need to memorize either of these two. So let me show you an example in which I don't even care to go back and look at these formulas. Okay, so let's say 20, problem 20. Radioactive radium. Radium-221, that has nothing to do with us, it's just the name of the radioactive substance, has a half-life of 30 seconds. Half-life, 30 seconds. How long will it take for 95% of the sample to decay? Now, when you read this problem, you'll say, this is hard. I don't even have, it appears that I don't even have enough information, right? So I'm told that a radioactive substance has a half-life of 30 seconds. Okay? If I'm talking about a radioactive substance, I will immediately have to write this. I know this is the model. So I'm told that the half-life is 30 seconds, which means when t is 30 seconds, this mass will be how much? Half of m0, right? So when t is 30 seconds, the mass is half of m0. m0 divided by 2 equals m0 e to negative r times 30. I didn't have to go back to any formula. I simplify. This is 0.5 equals e to negative r times 30. And I know how to find r. I didn't look at any formula, but I need to remember the model. So I apply natural log, and the right-hand side is negative 30r. So then r equals natural log 0.5 over 30 with minus in front. And this is what I got from the general case. But I don't need to memorize this. So then let's find r. So r is natural log 0.5, everything divided by, in parentheses, negative 30. So 0.0231. So r approximately 0.0231. Okay. So then the model becomes m of t equals m0, which is unknown, not given to us, e to negative 0.0231 t. This is what I needed, or what I obtained by simply knowing this. By simply knowing that the half-life is 30 seconds, I was able to determine the decay rate. Now I have to answer this. I am not given the mass of the sample, but I am asked how long it takes for 95% of it to go away, to disappear, dissipate in thin air. So how long it takes for the original to lose 95% of it. What is left? 0.05 of what? Exactly, of M0. That's it. Exactly. So 5% M0 equals M0 e to negative 0.0231 t. Exactly. So 95% of the sample has dissipated. We are only left with 5% of the original mass. And this is what we've been doing for 2 hours. Natural log 0.05 equals negative 0.0231 t. And then I'll find out how many seconds are needed for 95% of the whatever initial mass we have to go away. So natural log 0.05 in parentheses divided by, in parentheses, negative, oh, I can use the previous answer. I can't get a negative number. Oh, I didn't put a negative answer. Yes, that's why. Oh, okay. I can't get a negative answer. That's not possible. Okay, divided by negative 0.0231. When I try to be innovative, that's what happens. So 130 seconds approximately. 130 seconds is what this radium-221 needs to decay to only 5% of whatever we had initially. It takes 130 seconds. So 2 minutes and 10 seconds to lose 95% of it. Yep, that's what cooling soup, same thing.